Okay, differentiate y equals cos x from first principles. So if you remember, we choose a point on the curve, we call it point P. So it'll have an x coordinate, just a general x, and then of course the y value will be what we get from cos x. Okay, what you do then is you go further along the curve, a little distance across, okay, we call it h. So now q will be x plus h, yeah, and that's our x coordinate here, little h across here. Our y value then will be cos of x plus h, okay, because you put the x plus h in there, and you get cos x plus h. So we've got our q value and our p value. So if you remember then, with differentiation from first principles, you do the gradient of the chord PQ, and that will be y2 take away y1. So the change in y over the change in x. Okay, so the change in y will be my y2, which is all of this here, cos x plus h, take away my y1, which is cos x. This is my second coordinate, it's my x2, y2, this is my first coordinate, x1, y1. So y2 take away y1, on the bottom then x2 is x plus h, take away my x1, which is x. So we get, on the bottom obviously becomes h, x is cancelled. Now on the top, what we can do then is expand cos x plus h using what we know with regards to the compound angle formula in the formula booklet on page 6, I believe. So cos x plus h, compare it with cos a plus or minus b, if you remember, but you just open the formula booklet and you use the result that's there, so it'll become cos x cos h minus, then because it's a plus you choose the minus if you remember, sin x sin h, okay, and then minus cos x at the end there. On the bottom then you just divide by h. Okay, so now we've got a gradient of chord PQ. We're obviously interested in finding dy dx. If you think about it, dy dx is the limit of this, yeah? It's the limit as h goes to 0, and it's important to do that at this stage, okay? Because we want to now limit h to 0. We want to send h to be really small, okay, in this expression here. So we're not sending x to be small, we're sending h to be small. And what's really good then, when h is really small, we've got results for cos and sine using small angle approximations. So we know that when h is really small, cos h is 1 minus h squared upon 2. Okay, that's what cos h becomes using small angle approximations when h is really small. And even simpler, sin h just becomes h itself. And then cos x then, well, we're not doing anything to the x. Now, a bit of simplification is needed here, but you'll see that the cos x's will cancel, okay? So if I expand the top line, we get cos x minus h squared upon 2 cos x minus h sin x minus cos x. So if I expand that and put the h in front here, and you can see, as I said, that the cos x's cancel, okay? And then we can see there's a factor of h in each of these, so we could then divide by h. So h divides into this, so you get minus h upon 2 cos x, and h into that goes once, so h divided by h is 1, so you just get minus sin x when you divide through by h. And we've got that final expression here, and ultimately then we set h to be 0, to go to 0, and you get your expression for dy dx. Well, of course, if h is 0, that disappears, and you just end up with minus sin x, which of course is what we're expecting. Y is cos x, dy dx is minus sin x.